So that's better already, and we have a bigger key, but best of all is to combine all three techniques that we have: chaining, substitution, and permutation. Because chaining is so easily reversed at the end of the pipeline, let's put it first, and then substitute, and then permute. And if we take our meet me at the clock tower plain text here, apply those same strategies with example keys that we've used in previous slides, we get down to this ciphertext message that is much more random than all of our intermediate approaches. This message doesn't have any of the patterns that were in our original plain text, and a small change in our plain text causes a completely different result. All the letters end up being changed in our ciphertext in this case. So this shows how the combination of three simple techniques can get us to a more random result. This ciphertext can be mapped back to the plain text as long as you can reverse the individual steps. As long as you can reverse the permutation by knowing the number of columns that we use in a table-based permutation, say. And then the substitution step can be reversed by knowing the number of rotations that we applied in a Caesar cipher, say. And then chaining can be reversed by knowing the number of iterations that we did, the operation like plus that we use, and some initial seed value that we use to kick off the chaining. Then you can reverse that step and get back to the original plain text in this case. So you have to know all four of those things: the rotation, the column count, our initial value for chaining, and the number of times we went through the chaining. But of course the algorithms and the size that we use today were just meant to illustrate the concepts, and we can see that this simple case is insecure because the number of different rotations we have is only 26, number of different columns is 32, initial values is 27, because it wraps around after that, and the number of times you might go through, well, 10 is a pretty good number, depends on the message size, but it would be at most hundreds. If we say that 10 is the most times we're willing to iterate through chaining, then that gives us 200,000 or so possible keys, which is not a lot for computers, so a brute force attack could still probably figure out our message in this case. One of the things we're going to do to improve the strength of our encryption is to have a bigger space of key, have larger key sizes. So you can see from our example why we will care about the key size for our different algorithms. Another thing is that I've encoded these small messages all at once, taking the whole message and producing one ciphertext for the whole message. But more realistically, you're communicating streams of information over the network. You want to stream that data through and understand it piecewise as it goes through. So you will encrypt smaller pieces of the overall message as you go. That's going to decrease the diffusion over the overall message. And so you really want to make those block sizes as big as possible while still allowing a certain amount of streaming. So block sizes are going to be an important choice in our algorithm as well. And the kinds of block sizes that we're going to look at are going to be measured in bits as opposed to bytes. So we will be looking at 128-bit or 500-bit block sizes. So choosing larger block sizes is going to be better, but there's going to be trade-offs in terms of computation.